Welcome back to Differential Equations. In this video, we're going to be talking about fundamental sets of solutions. The fundamental set of solutions is going to be a tool to allow us to analyze two questions that are very common in working with differential equations: the existence and the uniqueness of solutions. We want differential equations to have solutions. We know that a differential equation will have infinitely many solutions. It would be nice if we could classify our solutions and know that we were talking about a specific solution or talking about two different solutions if they were written differently. We know that we can write initial value problems, couple a differential equation with one or more initial conditions in order to restrict the solutions. It would be nice to know that the initial conditions are going to give us a single solution, that the solution is going to exist, and that there aren't going to be more than one solution. So the ideas of existence and uniqueness are things that are studied extensively in the mathematics of differential equations. If you go on to study more differential equations at higher level mathematics, these are the kinds of questions that you're going to begin to study. For our purposes, we're not going to get into too much depth on these, but they are the ideas I want you to have in the back of your head as we move on. All right, so let me get my head out of the way and let's scroll the page a bit so that we can put in a few more definitions. A fundamental set for an nth order linear homogeneous differential equation. All right. So we are going to insist that we're dealing with a linear differential equation. We're going to insist that it's homogeneous. We don't care what order it is. We don't care whether it has constant coefficients or not. A fundamental set is a set of n linearly independent solutions. Remember, we saw previously this idea of linear independence comes up when we're talking about taking linear combinations. When functions are linearly independent, there is a unique linear combination that gives the trivial zero function. When they are linearly dependent, there are multiple options. We want to avoid that possibility because we're going to be taking linear combinations. I also want to remind you of the idea of superposition. Every linear combination of the functions in a fundamental set is also a solution. All right. Once again, that's something we've talked about previously. Just the nature of a linear homogeneous differential equation insists that that is going to happen. All right, that takes me to my claim. Every solution to a differential equation can be written uniquely as a linear combination of a fundamental set, or of the functions in a fundamental set. And I want to stress the idea here. I've talked about a fundamental set, not the fundamental set. Once again, for anyone who has studied linear algebra in the past, these are concepts that should be familiar to you. If you have a fundamental set of solutions, you can always use that to generate a different fundamental set of solutions. There are, in fact, infinitely many different fundamental sets of solutions for any differential equation. As long as you have one of them, you have everything you need. That's the power that we're talking about here. There are infinitely many fundamental sets. If we can find any one fundamental set, then every solution to the differential equation can be written as a linear combination of the functions in that set. And furthermore, that can be done in a unique way. Once again, for anyone continuing onward in mathematics, this is something that you can definitely study in more depth. If you've taken a course in linear algebra, a course in differential equations, and a course in mathematical analysis, the next step is to study the theory of differential equations. So that's something that can be interesting. It's a little bit beyond the scope of this course. So I can't quite prove this claim. I can't prove to you that every solution can be written as a linear combination of the functions in a fundamental set. I can, however, prove to you that given a solution written as a linear combination of the functions in a fundamental set, that, excuse me, that linear combination is unique. So for example, let's consider a second order linear homogeneous ODE. Let's give it two solutions, phi1 and phi2, which are linearly independent. And let's consider the function x of t given as c1 times phi1 plus c2 times phi2. All right. So again, I know that x of t must be a solution. I am claiming without proof that every solution can be written in this way. And what I want to prove is that if I take that same function and I write it as a different linear combination, let's call it k1 phi1 plus k2 phi2. And I claim that the only way we can do this is to get that c1 is equal to k1 and c2 is equal to k2. The proof of that is actually pretty straightforward. If I take c1 phi1 plus c2 phi2 and I subtract from it, or yeah, let's subtract from it, k1 phi1 plus k2 phi2. Well, I can rearrange this and I can write this as c1 minus k1 times phi1 plus c2 minus k2 times phi2. And then think about what I did. I took a representation of x of t and another representation of x of t, and I subtracted them. So I have a linear combination of these two functions equal to 0. And since phi1 and phi2 are linearly independent, the definition of linear independence says that the only way we can take a linear combination and have it equal to 0 is if the coefficients c1 minus k1 and c2 minus k2 are both equal to 0. And for c1 minus k1 to be equal to 0, that means that c1 is equal to k1. And for c2 minus k2 to be equal to 0, that means that c2 is equal to k2. All right, so it's not a proof of the entire theorem. Again, I know I've been harping on that, but I try my best to state things and not overstate things. This is not a proof of the entire theorem. This is a proof of one part. The fact that every function which is a solution can be written as a linear combination is a big deal in and of itself, but we don't have the tools to prove that just yet. Again, anyone who is continuing on to further study of differential equations, that's something that you will get to see. It's kind of interesting. I find it fascinating, but we don't have anywhere near enough time to do it this semester. All right, but instead, I want to build this up. For an nth order linear homogeneous ordinary differential equation, solutions are going to be in the form x of t is equal to c1 times phi1 of t plus c2 times phi2 of t plus dot 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 plus cn times phi n of t, where phi1, phi2 down through to phi n are linearly independent functions which form a fundamental set of solutions. Right? The important thing here is that we have n arbitrary constants, c1, c2, down through to cn. Another result out of linear algebra. This one is one that you're probably familiar with already. If you have n unknowns that you want to try to solve for, you need a system with n equations, one equation for each unknown. That's kind of fundamental in algebra. Most of elementary algebra, you look at situations where you have one unknown and one equation. But occasionally you deal with systems with 2 or 3 or maybe even more unknowns and systems of equations, usually linear equations. Conveniently, this is going to give us a system of linear equations, so we're good on that front. All right, to get the values of n unknowns, we need n conditions. X of 0 is equal to some x naught. X prime of 0 is equal to some x1. And we'll go all the way down to the n minus first derivative. Notice here the counting. It's a little bit goofy. We start at 0 and we go to n minus 1. If we could go all the way to n, then we would actually overdetermine our situation, and we would have a single point that would be our solution instead of a function. All right, so we're looking for n conditions, starting with the original function, the first derivative, the second derivative, up to the n minus first derivative. That is our n conditions. And based on what we know in linear algebra, this should give us a unique solution. So for a second order linear homogeneous ordinary differential equation, a times x double prime of t plus b times x prime of t plus c times x of t equals 0 with initial conditions x of 0 is equal to x naught, x prime of 0 is equal to x1, there exists a unique solution. Right? That is the idea that we come to. I didn't quite formally prove it, but hopefully I gave you enough evidence to convince you that that should be the case. And we can find that unique solution given a fundamental set of solutions and a couple of initial conditions. So, for example, if I'm looking at the differential equation, x double prime of t minus 2x prime of t plus x of t equals 0. We saw in a previous video that the functions phi1 of t equals e to the t and phi2 of t equals t e to the t are both solutions to this differential equation. We did not show that these particular functions are linearly independent. I encourage you to take the time to show that for yourself. But what I want to do is take a look at this differential equation along with the initial condition. X of 0 is equal to 0, and x prime of 0 is equal to 1. And so there should be a unique solution to this initial value problem. Oops, sorry about that. Pushing the wrong button. Sorry for blinding everyone. All right. So again, if you are not comfortable with it offhand, take a few minutes, look at these two solutions, prove to yourself that they are linearly independent. And then since I have a second order differential equation and two linearly independent solutions, I have a fundamental set. Use that to write a general form for every solution to this differential equation as a linear combination, and then use the initial conditions to see what happens. All right, take a few minutes, see what you can do with that, and I'll see you in the next video.